Alright, at this point, we have a clear understanding of how this process should operate and the behavior of normally open and normally closed contacts. With this knowledge in place, we can now move to the ladder program that meets the requirements for this process. We've linked the Start push button to X0 input pin of the PLC, the Reset push button to X1, the emergency switch to X2, the bottom sensor to X3, the top sensor to X4, the S1 sensor to X5, and the S2 sensor to X6. Similarly to the inputs, here's a visual representation of how the output pins are connected to output devices like conveyors, indicator lamps, and motors. Introducing the internal memories crucial to our ladder program, M0, M1, and M2 are single-bit memories capable of holding values of 1 or 0. Similarly, D0 and D1 are integer memories designed to store numeric values. In ladder programming, each instruction line is referred to as a rung. Let's now examine the impact of each rung within the program we've developed for this integrated box sorting process. Firstly, we will set up all the memory locations based on the input signals. Here's the initial rung. As you're aware, the emergency switch has a normally close contact that connects to the PLC's X2 pin. This indicates that a 24-volt signal is present at the X2 pin until the emergency switch is triggered. In this rung, a normally open contact is used for the X2 pin. This means that if the X2 pin reads 0 volts, it operates like a normally open contact. However, in this scenario, the X2 pin receives 24 volts as the emergency switch hasn't been activated yet. This implies that this contact remains closed until the emergency switch is activated. A normally close contact is utilized for the X1 pin. This indicates that the contact remains in its normally closed state until a 24-volt signal is applied to the X1 pin by pressing the Reset push button. Alright, now that we understand the contacts linked to X1 and X2 stay closed until the Reset push button is pressed or the emergency stop is activated, let's see what occurs when we press the Start push button. The contact linked to X0 closes since it is a normally open contact, causing M0 to go high. If the Start push button is released, the contact linked to X0 opens once again, resulting in M0 returning to a low state. However, this isn't our desired outcome. We want M0 to remain high even after releasing the Start push button. To achieve this, we can introduce a normally open contact associated with M0 in parallel with the X0 contact. This setup is known as self-holding or latching. Once M0 becomes high, the contact related to M0 closes, establishing a pathway for the signal to sustain M0 state, even if the X0 contact is open. So, it's crucial for the M0 memory bit to be in a high state to keep the entire process operational. If M0 transitions to a low state, the entire process comes to a halt. The bottom sensor is activated whenever any type of box is detected. This indicates that a box has reached the starting point of the sorting process. In this specific rung of the ladder program, if the X3 pin is in a high state, which is associated with the bottom sensor, the M1 memory bit is set to a high state as well. This action signifies that the system recognizes the presence of a box and signals the commencement of the sorting sequence. When both the bottom and top sensors are activated, it signifies the presence of a tall box in our sorting process. The top sensor is connected to the X4 input pin of the PLC. So, when both the X3 and X4 pin states become high, indicating that a tall box has arrived at the starting point of the sorting process, the M2 memory bit is set to a high state simultaneously. As we are aware, M0 can be set by pressing the Start push button and reset by pressing either the Reset push button or the Emergency Stop. Similarly, we require a mechanism to reset both M1 and M2. Here's where the role of S1 and S2 sensors comes into play. When any box reaches either the S1 or S2 sensor, it signifies that the sorting process for that particular box is finished. Previously, this box triggers the setting of the M1 and M2 memory bits to a high state. Therefore, when either the S1 or S2 sensor is triggered, we can reset both the M1 and M2 memories simultaneously. S1 and S2 sensors are connected to the X5 and X6 pins respectively. This rung illustrates how M1 and M2 can be reset by monitoring the states of the X5 and X6 input pins. Alright, now we understand that M0 being in a high state signifies the operator has initiated the process by pressing the Start push button. M0 transitions to a low state if the operator presses the Reset push button or activates the Emergency push button. If M1 is high, it indicates the presence of any type of box. Similarly, if M2 is high, it indicates the presence of a tall box. From this point onward, our focus will primarily be on these three memory bits. Regardless of the changes in X0 to X6 inputs, we can determine the process status by monitoring these memory bits. If we aim to count tall and short boxes independently, here's how we accomplish that. This instruction outlines the process. When a positive edge is identified on the X5 input, it signifies the arrival of a box at the S1 sensor. Positive edge refers to the moment when the voltage of the pin state changes from 0 volts to 24 volts. The C0 counter increments its value accordingly. Simultaneously, the counter values are transferred to the D0 register. The identical instruction is applied to obtain the count from the S2 sensor, as demonstrated in this rung. When someone presses either the Reset or Emergency push buttons, it triggers this rung. Specifically, this instruction uses the M0 memory bit as a signal to reset all counters, C0 and C1, and data registers, D0 and D1, back to their initial values of 0. The change in the state of M0, from a high state to a low state, the NC contact linked to it changes from open to closed, acts like a switch that resets these elements in the PLC, ensuring they're ready for the next cycle of counting and sorting. Moving on to the task of displaying these saved counter values, the steps are as follows. Choose a numerical display that matches your PLC specifications. Evaluate the communication protocol supported by your PLC and the chosen numerical display. Establish a connection by using appropriate communication cables to link the PLC and the designated display. Configure PLC to send the values from D0 and D1 to the selected displays. This ensures that the counter values are accurately conveyed and displayed on the numerical interface. Now, let's move on to the exciting part. We'll proceed to generate outputs based on the behavior of the configured memories. This section is dedicated to configuring our entry conveyor. When M0 is set to high, the signal can flow through it, energizing the Y0 output pin until M1 also becomes high. When M1 is high, it indicates that a box has reached the bottom sensor, causing the normally closed contact associated with M1 to open, interrupting the signal and halting the entry conveyor. The sorting conveyor must operate continuously, starting when the start push button is pressed and stopping only when the reset or emergency push button is activated. When M0 is in a high state, the sorting conveyor will be in operation. To activate the sorting arm and its belt conveyor, the integrated system must be in the run mode, which requires M0 to be set. Additionally, M2 should be in a logical 1 state, indicating the presence of a tall box at the top and bottom sensor's position. Similarly, to activate the warning lamp, the integrated system needs to be in the run mode, with M0 set. Furthermore, M2 should be in a logical 1 state, signifying the presence of a tall box at the top and bottom sensor positions. When the system is in the stop mode, signified by M0 being in a low state, the stop indicator should be illuminated. To achieve this, we utilize the normally closed contact of M0. When the operator presses either the reset or emergency push buttons, causing M0 to transition from logical 1 to 0, the normally closed contact changes from open to closed, activating the stop indicator. Similar to the other outputs, the emitter requires M0 to be in a high state to operate. The emitter should release boxes onto the entry conveyor only when the entry conveyor is running. If there's a box detected at the bottom sensor, indicating that M1 is in a high state, the entry conveyor should pause until M1 returns to a low state. Similarly, the emitter should also halt box emission until M1 is low. To meet this requirement, we employ the normally closed contact of M1 in this rung. When M1 goes high, this contact opens and halts the emitter. Okay, now that we've covered how to create the ladder program step by step, our next step is to see how to implement all these rungs in GXWorks 2.